For sure. The one that was just you. Oh yeah, I'll text you the link and come forward. That's like the previews, so you already know it's pretty cool. You didn't change this. I did that over the summer. Video out. I thought it was a YouTube link, but the preview and it's very helpful. That was funny, but not funny this time. I think after around 10 years, it's funny. You got not funny when we started doing all that tape stuff. I was gonna guess that. I thought I would find that you like, but I'm trying to download this and then I used that. What about like the old stuff? Oh yeah, that's great.
I remember my name. What is that?
You're not a true engineer. SKCD head.
So, okay, I think we should get started. So in the last lecture, we reviewed the important statistics regarding random variables. So given a random variable x, we know that this is kind of not a deterministic value. It can take many possible values. And how can we evaluate the properties of this x using some fixed constant? We'll review two important statistics regarding the random variable x. The first one is the expectation. So expectation is the weighted average of all possible values x can take. So basically, you can consider that this is the possible places that x can jump. And obviously, it is more likely that x takes value here, and less likely that x jumps far away. So we want to know, on average, what will be x? What will be the position of x? This is what expectation can tell us. So the definition of expectation is the weighted average of all possible values x can take, and the weight, it is the PDF, the PDF function, probabilistic density function. And we discuss how to compute expectation. In the first, the simple case that x is a discrete random variable. So for a discrete random variable, how can we compute expectation?
You sum the multiplication of each value times the probability.
Yeah, very straightforward. So for discrete random variable, its PDF, the probability density function, actually can be represented by a table. So this table, here is x, and here is the probability of x taking some value. So suppose it can take value 1, 2, 3 until n, right? So in this table, we have a corresponding probability P1, P2, P3 until Pn. Then the expectation for this discrete random variable is computed through the weighted average here, right? So the first value x can take is 1, and corresponding probability is P1, right? Weighted by P1. And the second possible value x can take is 2, and corresponding probability is P2. And we add them together until the last value, which is n, that x can take, and multiply with the probability Pn. This is a way to calculate the expectation for discrete random variable. And then what if the random variable x is continuous? How can we calculate the expectation? Yeah. When we're talking about continuous variables, we actually need to generalize the summation to integration. So integration is always you can see it as an extension for infinite summation. So if x is continuous, then we know that x has a continuous probability density function. So it is usually denoted by small f and indexed by this random variable x, big X. And here is the input of x. So this small variable, small x, indicates the input of the probability density function, nor is this function. So this probability density function actually determines the random variable x. So now if we want to calculate the expectation of x, this is continuous. Now what we do is to integral. An integral is over the entire domain that contains all possible values x can take. And then inside this integral, we multiply each value x can take and weighted by the PDF, the density function, and then do the integration. So that's the way to compute the expectation for continuous random variable. So this is the definition for the expectation. And another very important statistics associated with the random variable x is what we discussed in the last lecture. The expectation just shows on average x will appear. Right? Then what is about another property or statistics that can describe x? Yeah, variance. Because x is a kind of dynamic variable, right? It can jump here, can jump here, can jump here. So naturally, we would like to know, on average, how far away x can jump from its expectation. That's how we define variance. So what is variance? So can any of you look at this board? Is it okay for you to see it clearly? Okay, that's fine, because later I will use this projector. So just leave it here. Okay. Then what's the definition of the variance? What's the definition of variance on that?
It's the expectation of the square of the difference between the value and the expectation of it.
Yeah, exactly. So first, variance is another expectation. The second, the variance is a special expectation for what? For the square distance, all possible square distance between the value x take and its expectation. So this is the definition of variance. So and of course, we have shown that this expectation, this definition can be further. From this, we can further derive that the expectation is actually expectation of x squared minus square of the expectation. It's a very interesting result. And then the next question would be how can we compute the variance for different types of random variables? If x is discrete, how can we compute the variance? Similar to the computation for expectation. So this is still a weighted average. So we just, of course, we need first to calculate the expectation of x itself from this table. And then we do the weighted summation, right? And inside this summation, now each value of x is replaced by the square distance. And then weighted by each probabilities. Each probability corresponding to different values in this table. It's It's pretty straightforward if you practice. And then what if we want to compute variance for a continuous random variable? An idea? It's a similar thing to expectation, right? When there is a continuous random variable, of course we cannot do the finite summation. We need to generalize to integration. So then the variance is computed through the integral. The integral still covers the entire domain that contains all possible values of x and k. That is sample space of x. And inside this integral, we compute each value, the square distance between each value x and k, and the expectation, right? The square distance, and weighted by what? PDF. Weighted by PDF. That's the way we calculate the variance for the continuous random variable. So basically, it is a straightforward generalization from finite discrete values to continuous values. Just replace the summation by the integral. So the variance and the expectation are the most two important statistics to describe a random variable. But in addition to expectation and variance, there are also other types of statistics, which we're not gonna cover in this class. But I can give you a few examples, like moment. This kind of statistic called moment. Expectation of x is called a first order moment. And the second order moment is defined as expectation of square of x. So you see that the second order moment is different from variance. Because variance is actually the second order moment minus square of first order moment. And of course, we can generalize this moment to nth order moment. The expectation of x to the n. But among those statistics, the most commonly used and people care most are the expectation and variance. To show that how it is important, let us look at a very commonly used distribution or type of random variable called Gaussian random variable or normal random variable. So Gaussian random variable, if x is a Gaussian random variable, means that x is continuous. And the PDF of x has the following form. So 1 over square root of 2 pi sigma squared exponential 1 over 2 squared x minus square. So this is the PDF of the Gaussian random variable. And we can say this PDF is actually determined by two parameters. One parameter is mu here, right? And the other parameter is sigma. But what does mu and sigma square mean? It actually means the expectation of x and variance of x. So you can show that if you do the expectation of x by the integration, right, with respect to this PDF, you will see that the expectation of x is exactly mu here, and variance of x is exactly sigma squared. So it means that if I know a random variable is a Gaussian random variable, or normal random variable. The two things, the two names are the same thing. Then, as long as I know the expectation of our random variable and variance of random variable, we can completely determine the random variable x. Meaning that we know the PDF. As long as we know a PDF for random variable x, actually we know everything about this random variable x. And Gaussian distribution will be used again and again in your future data mining or machine learning class or applications. So you can see this such an important random variable. Its distribution is totally determined by these two statistics, expectation and variance. And there's a special type of Gaussian random variable called standard Gaussian random variable. The standard Gaussian random variable has expectation to be 0. Means mu is 0 here, and the variance is 1. So this is called standard Gaussian random variable. So we can say the standard Gaussian random variable now has a very simplified form. So it is 1 over square root of 2 pi exponential minus 2 x squared. It's an elegant exponential form. So what's the shape? What's the shape of the standard Gaussian random variables PDF? Maybe some of you have already known that the shape of the PDF of Gaussian random variables is like a bell. And it is symmetric bell. And the center is at the expectation of the random variable. And variance determines the width of the bell. And of course, for standard Gaussian random variable with 0 mean, right, and variance being 1, that means it is centered at the origin. And it has a span which corresponds to variance 1. Now I can simply, I want to show you a few lines of Python code to draw the PDF and the CDF for a Gaussian random variable. Is it clear for everyone and for you? If it's too small, I can.
You'll make it bigger.
Make it bigger. Okay. Is it better?
Yes.
Okay. So let me give you a few, just a simple illustration of this code. This code is really, really simple. So in the first few lines from line 1 to line 5, it's just a Python command that import the necessary library to draw the plots and to compute the PDF function values and CDF function values. So you see the matplotlab, as the name suggested, it is the lab which finished the plotting. And the line 3, scipy.stats, is a kind of statistic library. This scipy library is very famous. Using Python to do the linear algebra and the statistic stuff, you will always have to utilize this library. And this library implements a lot of computations regarding various distributions, such as Gaussian distributions, gamma distributions, include also Laplace distributions, which you are required in to draw such kind of plot in with PDF. And then another very important package or library is called NumPy. So NumPy is mainly used to the complex matrix computations or linear algebra computations, such that you don't need to do it element by element. It is very efficient. And finally, is the math library. Now, line 7 and line 8 actually set the expectation and variance of our standard Gaussian random variable So later we can change the value of the expectation variance and say how they affect the shape of the PDF and CDF. And the sigma here, we actually, this line of code is to do the square root of the variance. So the square root of variance is actually what? Yeah, standard deviation. I want to maintain the same unit as the expectation. Remember, variance is double, right? We take a square distance. If we want to maintain the same unit as the expectation, thus we take the square root, the standard deviation. And now, this line of code is trying to generate some input for the PDF function and the CDF function. So it tells us that I want to generate 201 points between the segment -3 to 3. I want this point to be equally spaced. So we call this function. Now later, when you play this code, when you run this code, you can debug it and say what will be the value of x. X finally turns out to be a vector of those inputs. And then the following 3 lines are the plotting procedure. So the first line 12, it calls the plotting function, and here x is the input, and here we say this is the PDF. So norm is incorporated in line 2. Or in line 3, you can say from the Sybase stats library, we import the library to compute everything regarding the normal distribution or standard normal distribution. It is also called Gaussian distribution. And then we call the norm library, PDF function of norm library, to compute the PDF function values for the given input set x. And we need to specify the mean of our normal distribution and the standard deviation of our distribution. So here could be, say, x, and this part is a corresponding PDF function value for each element of x. So actually this is x and this is y, and then the remaining 2 parameters actually designate the style of the line. And line width is 2, and label is 1. And similarly, in line 13, we plot the CDF function values for each element in x. So here we can see here is CDF, and then line width and label, and finally we put the legend. So this is a logical code. And now let us look at. Is there any question about this piece of code?
This generates a graph. This is going to generate a graph that will pop up when you do it?
Yeah. When you run it, it will pop up a graph and show you the curves. We'll do it immediately.
That's the word normal means normal distribution.
Yeah, normal distribution. But you can change it. You can change. Yeah, it's normal. It's normal. Of course, you can. If you check the grammar manual of Python, actually you can redefine this name. Usually we use norm, or you can change it as normal or whatever, whatever. Any other questions regarding this piece of code?
Will this norm library also have a function to integrate with PDF?
Yeah, it implements the way to calculate that, like CDF, and how do you do the integration? You don't need to worry about that. As long as you call this function, you get values. Any other questions about this? Okay, great. And then now let us look at what is going to produce through this piece of code. So, okay, so this is the code, and then let us run it. So now we can see the figure, right? So this blue curve are the shapes for the PDF. Right? You can see it's like a bell. Because this is a standard Gaussian distribution, mean that the expectation is 0 and the variance is 1. So you can say it is centered at 0. And this is CDF, cumulative density function. Remember, CDF is the integral of the PDF to the specific input. So CDF is always monotonically increasing. And CDF cannot be bigger than 1. So we can say when x increasing, the CDF function value is approaching 1. Then we can say if we set up different values of mean and variance, say we can change mu to be 0.5. So now it's not a standard Gaussian distribution anymore, because the mean, the expectation is not 0. It is now I set it to be 0.5. And then we run this code again. What can we find? We say the center of this bell curve now locates here, 0.5 here. And also it changes the position of the CDF as well. And then we can further make some changes on the variance. Remember, we just discussed that variance actually determines the width of the bell shape for the PDF. Right? So now let us change it, make it smaller, like to be 0.1. And we run it. Now PDF becomes much narrower. It is intuitive because you see the smaller the variance, the range x can jump is shrink, right? And also the corresponding CDF shrinks as well. So I recommend you to, because this piece of code is showing the cost material. So I recommend you to copy this code in your Python terminal and run it and play it to have a sense about the properties of Gaussian random variables. And also, it will be easy. It will be very easy to modify this code to finish your homework problem, draw the PDF for another type of random variable. Okay. Any question?
Is this code going to be posted online anywhere?
It is already online.
So it is, okay.
Yeah, it's come to my house course web page and download the course materials PDF. But inside the PDF, the code snippet is there. You just copy it and run it, you'll see the figure. Okay. Yes. This is okay, we need to use the full. Okay. So next we're gonna discuss an important rule, the definition. What is the definition of the conditional probability?
Probability with M and D over the probability
the
of D.
Drawn probability of M and D, right? Drawn probability means that the probability that both M and D happen and then divided by the marginal probability of D. The base rule tells us that this conditional probability can be calculated from the reverse conditional probability, namely from the conditional probability given M, D happens. And how do we compute it? This is a formula. So to compute this conditional M given D, right, it is equal to D given M multiplied with the marginal probability of M, and then divided by the marginal probability of D. This is called base rule. So these two conditional probabilities are in the opposite direction. So we can first verify this base rule through a simple example. Say we have two events M and D. Let us write down the example drawn probability table. So So here's m equals to 1, m equals to 0, and d equals to 1, and d equals to 0. And suppose their John probability that m and d both happen 0.25, 0.5, 0.2, and 0.05. So now let us first calculate the left-hand side, the conditional probability that m given d. We use the definition. So conditional on d happens. What items should we look at in this table?
Probability of D and probability of M union D.
Yeah. So what we need to look at is just the case that d happens, right? Because it's conditional on d. So we only need to look at this row. Right. And then conditional on d happens, m happens. So this is m happens, d happens, right? So this would be 0.25, and then normalized by the condition that d happens. We do the normalized meaning that we sum the case that when d is 1 and m happens and m not happens. So it is over 0.25 plus 0.5. So it's pretty straightforward, which is 1 over 3. Because this is 0.75. 0.25 over 0.75, which is 1 over 3. Any question at this point? Okay. So now let us verify the right-hand side. So to calculate the right-hand side value, so first we need to know the marginal probability of m. So what is the probability that m happens, no matter whether d happens or not?
Zero 0.45.
0.45. How do you arrive at a number?
You add together the m equals 1 or d equals 1.
Great. We only need to look at the case that m equals 1, right? Because we care about the marginal probability, we don't care about the case d equals to 1 or 0. So we add them together. So we get the marginal probability, which is 0.25 plus 0.2, 0.45. And then the second term we care about is the reverse conditional probability that given m, the probability d happens. And how can we compute that? So this is conditional on m happens, right? So now that is conditional on m happens, we only need to look at this column. And again, when m happens and d happens, its probability is 0.25. But now it is normalized with the case that m happened. So we need to add these two terms together. So now we get 0.45. And then what is the conditional, or what is the marginal probability of d? This term.
0.75.
Yeah, we only need to look at this rule, right? Because because this is a case that d equals to 1. And to remove the effect of m, we need to add all cases relating to m. So now we get the marginal probability of d equals to 1, which is 0.25 plus 0.5 is 0.75. Now we combine these three terms according to right-hand side. Then we obtain, so the PM is 0.45 multiplied with PM given D, which is a PD given M, which is 0.25 over 0.45, and in the denominator it is marginal probability of D, which is 0.75. So now this one cancels, and finally will reach 103. So through this simple example, we can verify the correctness of Bayes' rule. It is quite straightforward, and actually, we can also directly prove this Bayes' rule according to the definition of the conditional probability. So basically, we know that according to the definition of conditional probability, this is the drawn probability of M and D divided by the marginal probability of D. Right? This is the definition. And similarly, if you want to look at the reverse conditional probability, that is D given M. What is the reverse conditional probability according to the definition?
Probability of M and D over probability of D, or M?
Yes, yes. So similar. Yeah. And now, so the second definition, we can rewrite the drawn probability of M and D by the product of the probability of M multiplying this conditional probability of M given D. This is a direct result from the second definition. And now simply replace this one by this one in our first definition. And then we can arrive at our Bayes rule. So it's pretty straightforward. You just need to write down the two definitions and then manipulate the terms and then replace the drawn probability with this multiplication and substitute into the numerator. We get the Bayes rule. But obviously, using Bayes rule to do the computation is kind of clumsy. It's kind of unnecessarily complex. Right? As we show in this table, computing the left-hand side is direct. It's straightforward. But if you compute the right-hand side, you have to compute at least 3 values. So this is kind of unnecessary. It's not very interesting. And then how can we apply Bayes rule? Actually, Bayes rule is really used to diagnose or inference, given some accidents we want to trace back the possible reasons. Then Bayes rule will become very useful. So let us look at one example here. Suppose I just purchased a car, a new car, brand new car. But after 3 days, I found, okay, there's a crack in my windshield. That's very bad. So let me denote this bad event by W, meaning that my windshield has a crack. And what I want to do now is that I want to know which factory assembled the car. And then I go to that factory and argue with them, ask for replacement or extra compensation. And how should we do that? Suppose we know that all the cars in the state of Utah are assembled by 3 factories, factory A, B, and C. And from mathematical language, how can I identify which factory assembled my car? An idea? Using the probabilistic framework we just learned.
Assignment number?
Assignment number? Yeah, assignment number, yeah, of course. And then, according to what we can make a conclusion that it is in factor A, most likely assembling the car, or factory B most likely assembling the car.
Expectation of.
Expectation, okay.
Wouldn't you need the probability that A, B, and C would create a car with a cracked windshield? Is that
Yeah, it's
what-
close. It's kind of close. But here, to do such kind of inference or diagnosis, we'll use conditional probability. So basically, I want to identify, I want to know, given my windshield crack event, what's the probability that factory A assembles the car? And what's the probability that factory B assembles the car given the windshield crack? And what's the probability that factory C assembles the car given this bad event, the windshield cracks? And then we can compare the three conditional probabilities. And then we pick up the maximum one. If this conditional probability is the largest, then most likely it is because factor A assembled a car that leads to my windshield crack. And then I go to the factor A, argue with them. So this is a mathematical procedure that how to infer the root cause for this bad accident. Or maybe not that severe, maybe it's just bad things. So the next question is that how can we compute this probability, this conditional probabilities? So first, to compute it, I look at some reports or statistics. I found that, okay, among all the cars in the state of Utah, 50% are assembled by factor A, and 20%, 30% are assembled by factor B, and 20% are assembled by factor C. So what does this tell us?
Probability of A.
Yeah. It actually tells us the marginal probability. So probability, that means the probability A, the car is assembled probability A. The car is assembled by factor A, the probability is 0.5. And the car was assembled by the probability assembled by factor B, its probability is 0.3, and also 0.2. And then I continue to investigate the report. I found a report that among all the cars assembled by factor A, 1% of cars will have windshield cracks. So what does this tell us? Yeah, this is not a conditional probability, but it's given that is the condition we change, right? So the condition is that given the car was assembled by the factor A, it has a crack. The probability of it has a crack is 1%, which is 0.01. And similarly, I found a report saying that among all the cars assembled by factor B, the chance to have a crack is 0.1, 10%. This is pretty high. So using mathematical language to encode this message, it actually says, given my car was assembled by factor B, the chance of the windshield crack is 0.1. And later we found that, similarly, I found that among all the cars assembled by factor C, the chance 2% of cars have windshield cracks. So that means this conditional probability, even C assembled car windshield crack has a probability of 0.02. And now, according to this marginal probability and this conditional probability, using Bayes' rule, we can go back to this reverse conditional probability. How can we compute that? According to the Bayes' rule, given the windshield crack, factor A assembled in a car is the probability of the A assembled car, right? Multiplying with the conditional probability that given A, there is a windshield. Remember, these two are reversed. And then divided by the marginal probability of the windshield crack. So this is Bayes' rule. And similarly, to compute the conditional probability of W, given W, B, follow a similar procedure. So now we can try to compute. So we know PA, the probability that A assembles my car is 0.5, right there. And then the conditional probability that given A assemble my car, there's a crack, the chance is 0.01, and then divided by the marginal probability of PW. And right now we don't know the general marginal probability of the windshield crack. Let's just put it aside. And similarly, we can compute the conditional probability that B given W by marginal probability of B and W given B, the reverse conditional probability over PW. And now we just replace it with the number, which is 0.3, and multiply with 0.1 and divided by PW. And similarly, C W P C times given C divided by PW. And let us just replace the number, which is 0.2 multiplied 0.02 over PW. So now, using Bayes' rule, we know how to compute this conditional probability. Now comes a question. Do we really need to know the marginal probability of the windshield crack? Why? Yeah, exactly, right? Because we want to find out it is which factory who should take the responsibility. I don't really care about the exact number, exact value, right? I just want to compare those conditional probability and find out the one with the largest probability, and then come to them. And because PW here is just a positive number, because the probability must be bigger than 0, 0 and less than 1. So the comparison won't be affected by PW, so we can just throw it out. So for the first conditional probability, the C, right? The factor C assemble my car given the windshield crack, which is 0.004 over PW. And for A, it is 0.005. 0.0. Oh, sorry, 0.004. 0.005. Yeah. And this is 0.03 over PW. So now we can see which factory has the largest probability, conditional probability. It is factor B, because this is 0.03, and this one 0.004, this 0.005, much smaller than this. And then, from this result, I can know that, okay, it is very likely because the factor B assembled the car, and it causes a windshield crack, then I come to the factor B. So this is one typical scenario where we use Bayes' rule to trace back the root reasons or causes for some particular accident. So it's very simple, very straightforward, but it's very widely used. Like in artificial intelligence, maybe some of you have taken that kind of intro course. So there is a very important invention in artificial intelligence called expert system. So what is expert system? When you are given a very complex system like power system, like spaceships, what if some part has some malfunctions, right? Or even some bad accident happen? And then how can I infer it is which part or which software that leads to the accidents? Can we use automatic method? Basically. Although this kind of system is much more complex than this windshield crack example, because we could have like thousands of, tens of thousands of causes, and they are coupled together to determine the output of the system. By using a similar modeling trick, we can compute the conditional probability for each possible reason or causes, right? And find out the largest one, and then investigate. This is an example showing the practical usage of Bayes' rule. And then let us relate Bayes' rule to the data science and machine learning. So how can we apply Bayes' rule in the data science and machine learning? So first, in data science and machine learning, there are two important concepts. Namely, model and data. So basically, model you can treat it as some simple patterns or hidden patterns, which are not obvious, which are hidden. And data is some observations. Observations actually are the patterns corrected by some noises. So nearly most data science and machine learning tasks is to recover the underlying pattern by looking at those noise observations. So later I will give you a few examples about model and data for different problems. So then how can we build up a mathematical framework to do the estimation or to do the finding of the best pattern given observed data? We need to utilize the Bayes rule. So basically, the general learning procedure or mining procedure or whatever can be written as I want to find the best model such that the conditional probability given observed data, this model has the largest conditional probability. So basically, it is a maximization problem. So you can consider, okay, there are a set of possible models, right? And for those set of possible models, we have a conditional probability that given observed data, and this model has a probability, right? And we just look at all the conditional probability given data and find out the model with the largest conditional probability. So this optimization or searching procedure is called learning or mining, whatever. And then how can we do this maximization procedure? We can utilize the Bayes rule. So according to Bayes rule, to compute this conditional probability, namely given the observed data, the model M, the probability of M, is the marginal probability of M. And then the reverse conditional probability, that is given the model M, the probability of D, the data D, and then divided by the marginal probability of D. And here we can observe that because this is the marginal probability of data D. And it has actually integrates all the effects of different models. So now it has nothing to do with models. So to models, the marginal probability of data D is actually constant. And that is between 0 and 1, some constant. And now, to maximize the conditional probability, M given D is essentially to maximize the numerator here, right? We don't need to care about the denominator because the denominator is just a positive constant. The value which reaches at maximum of the numerator is exactly the same as value which reaches the maximum value of the conditional probability. So actually we don't need to consider this. Why this is so important? Because in the future we will see that the computation of this marginal probability for data is really tricky, very hard. This quantity is usually known as model evidence or whatever. And to compute this, people have invented a lot of approximation methods, a large family of research areas, and still active right now. But fortunately, when we want to estimate some model, we want to find some best models, we actually do not need to care about the marginal probability of the data. So now, we know that to find out the best model, we only need to find out the maximum value which the best model M, which has the best value of this production term, and we call this best model, by maximizing the production between the probability of M and the probability that data D given M, called maximum A posterior estimation. Or abbreviated as MAP estimation. This is called MAP estimation, maximum A posterior estimation. Why? Because this is essentially to maximize the conditional probability of M given D. And this conditional probability is usually referred to as posterior distribution. Why? Because the marginal probability of M can be considered as some prior knowledge and prior experience of M. And now we want to look at, after we have seen some observed data, what will be the distribution of M? So why this is called posterior distribution. And if we want to, if we obtain our model by maximizing the posterior distribution M given the data, then this estimation is called a MAP estimation. This is one kind of methods to do the model estimation. But there is another type of methods to do the model estimation. It's called maximum likelihood estimation. So what is maximum likelihood estimation? So first we need to know what is likelihood. Likelihood is this. So given a specific model, what is the probability of the observed data? This is called likelihood. So likelihood is a probability term, or in other words, probability density term. So it's very intuitive because the more likely it is this model will generate this data, the higher this probability term. So this is called likelihood. If when we estimate our model, we ignore the effect of the probability of M, namely we ignore our prior knowledge about the model M. Or in other words, we simply treat all different types of models equally. So PM will be a constant. Then our maximization procedure, which is maximize the likelihood. So this way, our estimate model is called a maximum likelihood estimate, abbreviated as MLE, maximum likelihood estimate. And maybe someone of you has already taken a statistics class to know the maximum likelihood very well. But there's a connection between the maximum likelihood estimator and the maximum a posterior estimator. For the maximum likelihood estimator, there's no marginal probability of M here. Any question on this part?
Is both of this Bayes inference? Sorry. No. I asked the wrong question.
You can say it's a Bayes inference. So the essence of this inference is not at here, whether you use maximum likelihood or you use a map estimation. So Bayes inference actually requires you to calculate the posterior distribution. So we want to find out some posterior distribution. But this is kind of beyond the scope of our class. So right now we only need to know, okay, how Bayes rule is involved in a model learning, training, estimation, mining procedure in data science machine learning. This is how Bayes rule is applied. And how it connects to the very commonly used maximum likelihood estimation. And before we go to some detailed examples to show how we use this map estimation or maximum likelihood estimation to estimate models, let me give you a few examples of model data so that it won't make you feel kind of confusing. So for example, model M would be some point. This is just a small circle. It's invisible. You don't know that. And the data we observed is just some noise observations surrounding this model. And then our task is that by giving this process, I mean the noise observations, can we infer the model, namely this point. This is one example. Another example is called linear regression. Let's just talk about it in the two-dimensional space. So the model could be a line, just a line. But actually it's not observed in our data. What is our observed data? Our observed data is kind of a set of points which are close to the line. Then our data mining task or machine learning task or whatever task is want to estimate or find out this line given this noise observations. So you can see all this actually some pattern, some hidden patterns. And data are the noise observations of those patterns. And our task is to remove those noise and recover the pattern. So now let us go through two examples. One is for maximum likelihood estimation, and the other is for map estimation. So suppose our data is a set of data points, which is 1, 3, 12, 5, and 9. And our model is actually a real number. So our model belongs to the real value domain. And given each data point belongs to our data, we assume the likelihood of this data point given the model M. This likelihood, this is a conditional probability that given M, xi, is a Gaussian distribution, as we just mentioned. This Gaussian distribution with the model M as the expectation and variance to be 4. So this is our setting of the problem. And now the problem is that given this a few observed numbers, can we infer the model M? How can we do that? Using maximum likelihood estimation. This is maximum likelihood. Remember, maximum likelihood is defined as take the maximization over the likelihood function. So we only need to write down the likelihood function, namely the probability of the observed data given M, and then find out the maximum. Find out the best M which has a maximum value. Then we'll get our estimated M. So now we just use this framework to do the estimation. First, we need to write down the likelihood. That is the conditional probability given the model M, what's the probability or PDF for the data D? What's this? This one. This is a. So here I just write it. I didn't write down the explicit PDF. So explicit PDF is what? According to the Gaussian random variables PDF, it is 1 over square root 2 pi and times 4, right? And exponential of 1 over 2 multiplied 4 and m and xi minus m squared. Right? This is a PDF for the Gaussian random variable, and here 4 corresponds to the variance, and m corresponds to the expectation.
Where did we get 4 from? Did we just come up with that? Or?
This is a, yeah. Oh, you mean why we assume it's a Gaussian random variable?
Or why are we assuming variance is 4?
It's just to come up now.
Oh.
Yeah, of course you can also assume the variance is unknown, but this is not a problem. It's more complex, but it is still doable. So now we know that given the model, the single points likelihood is this. Right? And now we assume that given this model, all the points in this data set are conditional independent. So with that being said, this likelihood is a production for the likelihood of each data point, xi, d, data d, the production of the likelihood for each single data point, which is the production of those PDF for each data point. And we write out as 8 pi exponential to 1 over 8 and xi minus m squared. So this is a likelihood given the model M and the data, the probability of data. And now to do the model, to do the maximum likelihood estimation, our task is to find out M, which is maximization of this. Let me write it. So the best model is the value that maximizes this likelihood. This is called maximum likelihood estimation. And how can we do that? M is a variable here. We want to maximize this this term. How can we do that? Take gradient, set it to 0, and solve that. But take gradient over a production of terms is actually problematic. It's not very convenient. Because we say x1, x2, and x3 take the gradient. You have to use like dx1 plus x1 times x1, x2 plus x1 dx2 x3, right? You have to write quite a few terms. So it's really not very convenient for computation. And for many complex models, estimation problem, it's not that easy, like exponential multiplication of exponential. It's often very complicated. And you're multiplying with many very small numbers between 0 and 1. And then the multiplication, if the multiplication is very long, then the value will approach 0. And that means when you do some numerical, you use some numerical method to do the optimization, it will bring in numerical instability. So a commonly used trick is to take logarithm over the likelihood. That is, we want to maximize the logarithm of this likelihood. Because log function is a monotonically increasing function. So if you take a logarithm over one function, you'll maximize it. It won't change the optimal point. Any question about this one?
So for the likelihood, the D is always a set of number, a set of value, and N is always an equation.
M is kind of a set of another numbers, but you do not know that. You want to ask me.
Okay, but since I hear the M is normal distribution.
M is not normal distribution. M is number is the mean of normal distribution.
Oh.
So given M, xi is sampled from a Gaussian distribution, right? Determined by this PDF. And I want to infer what is the profit value for M. Any question?
And the way we calculate the likelihood is always this way. This is the way we usually use this equation to calculate the likelihood.
Yeah, we really assume that given the model, different data points are independent. But it could be the case that we also model the correlation between the data points. But this ID assumption, independent identically distributed assumption, is very commonly used. Any question at this point? Okay. And then when we take logarithm, because log is a monotonically increasing function, it doesn't affect the maximum. I mean the value which reaches the maximum. So when we take logarithm, now it becomes a summation. And then the production immediately becomes the summation over each data point. So you can
Sorry,
simply.
that's really hard to read. Sorry.
You mean which line is hard?
The one you're erasing, like I couldn't make out half of it.
Here?
No, the one you just erased. When you took the log of it.
We'll take log. Yeah, I want to write it here.
Oh, okay. Thank you.
So let me write down the log likelihood, the D, given model M, right? So we take logarithm over the production, it immediately becomes the summation. Summation over each sample in the data, each point in the data set. So you take logarithm over this. So it is a logarithm 1 over square root of 8 pi. And then minus, because when you take logarithm here, the exponential cancels, right? So now it becomes minus 1 over 8. Xi is the data point, ith data point, and minus the model M, and take square. And now we want to maximize this log likelihood to find out the best model M. And what should we do is that we just simply take a gradient and set the gradient to 0. So how can I take the gradient? This is a constant. So this is the gradient is 0. And for this one, what is the gradient? This is square term, right? Yeah. So the gradient would be 2 times xi minus m. Because there is minus 1 in front of m, so we must multiply with minus 1. And outside is 1 over 8. And outside this is summation. So this is a gradient. This is simple.
Remind me what the production does. Like what effect the sign that's the product, you know, the almost pi sign, but straight. What does that do, and why is that just that?
This is a PDF for Gaussian random variable.
No, the figure you're labeling as production. So you said the production of the probability, yeah.
Here?
Yeah, the production part of that. What effect does that have on the probability of, or on that conditional probability?
So we assume that given the model, each data point is independent. So basically it says x1, x2 to xn, right? This is our data D, given M. They are independent. What does independent mean? It means the probability is x1 given M multiplying x2 given M until xn given M.
Oh, so it's just a summation, but not summing, it's just a multiplication. Never mind, okay,
Yeah,
I figured out.
This is a multiplication. We
Yeah,
haven't arrived at the summation. Summation is that we take logarithm of that.
Right. And then when you take the log of both sides, that term no longer.
Yeah. So this one is this one, right? Just a simply.
Sure. Yeah.
And now we take logarithm over that. If I take logarithm over this, now the production becomes summation.
Okay.
Yeah, because this is the property of the logarithm, right? Log A times B is log A plus log B.
Got it. Okay.
This is a nice property of logarithm. So when we take logarithm over a production of several terms, it immediately becomes the summation of the logarithm for each term. And then because it's a summation, then we can take the gradient for each term independently and add them together to get a gradient. This is a common used trick to for the computation. Any question at this point? Yeah, I guess this example is listed in the course material. I can just practice after the class and follow this process. I believe this is pretty straightforward. You just use calculus yourself, and then when you take the gradient, you say this is a gradient, right? And then you set this gradient to be 0. This is a gradient. This is a gradient, and you set this gradient to be 0. You finally end up with our MLE estimator to be the average, simply the average. Of the data points in D. That's pretty interesting. You see the MLE estimate for the model M, namely the expectation of this Gaussian random variable. Random distribution is simply the average of the observed data. So finally I want to give a very quick review for another quick example for using the map estimation. So very simple. So assume our model space only has 2 models, M1 and M2. And we do assume the specific form for the conditional probability that D given M. So just assume that, okay, given model is M1, the probability of data D is 0.5. And given the data D, given the model is M2, the probability of the observed data is simply 0.05. And also, we now cares about the probability of M. So the probability of M is like this. So the probability of M equals to M1 is 0.25, and probability of M is M2 is 0.01. So now we want to find out the best model by using the map estimation. How can we do that? So the map estimation is to find out a model which maximizes the conditional probability, that is the given data D and the model, right? So as we just showed, this is equivalent to maximize the probability of M multiplying with the condition probability, that is the likelihood, E given M. Now just look at, because we have two models, M1, M2, right? So we can simply look at the value when M equals to 1 and M equals to 2. So when M equals to 1, then PM is 0.5, and the likelihood is, PM is 0.25, and the likelihood is 0.5. That is M equals to M1 given D. So this is the case that M equals to M1. And in the case of M equals to M2, the probability of M is 0.75. And multiplying is, here's 1.75. And then the likelihood, given model is M2, the probability of data is 0.01. And now to find out the best model, we just need to compare the two values here. So for M equals to 1, M equals to M1, this value is 0.125. And for M equals to M2, this point is 0.075. So which one is larger? The first one. So that means if we use map estimation, we will choose M1 as our best model. But if we use maximum likelihood, we need to wipe off the PM part and just compare the likelihood.
I think that was plus 420.
Yeah.
Oh, okay.
Yeah, we just passed 1 minute. I just want to finish that.
Okay, I just want to check.
Yeah. So in this case, we'll find out M1. But if we are not looking at the, we're just looking at MLE, maximum likelihood estimation, we just wipe out PM and find out the model with the maximum likelihood, which is still M1 here. Of course, we can manipulate the network to change the result. Okay, so I guess after giving the two examples, you have enough knowledge to solve all the problems in homework 1. And if I'm not wrong, next Monday will be Labor's Day, and so there will be no class. And see you on next Wednesday. And also, because later I will have a class meeting, so if you want to go to the office hour, we can go to the TA's office hour instead. Okay.
Excuse me, teaching assistant. I have one question. So, do you remember Clark Henry's problem? sorry. 现在这个结果，上面那边就来，那边就好几家。